So 1.2, so kind of the limits of a function. Limits help us compute velocity and other rates of change. Today we'll be looking at basic understanding of limits. We're not doing much applied today, more just understanding the basic concept of a limit, okay? So before we get into the actual limit part, we're just going to look at this function, okay? And we're going to check out what this function is doing as it's right before 3 and then right after 3, okay? So the limit function is what's it doing at that point. Now, it may not be defined at that point, but it may be approaching a number that we can call its limit. Okay, so for example, I'm just going to fill out this chart real quick. So I'm going to look at 2.5, 2.9, 2.99. Okay. And, okay. So these are all from 2.5. I'm getting really close to 3, but just under 3. So we're just going to look at what this is approaching. So it's 0.6. I'm going to go to 3 decimals. To 6 decimals, sorry. So 0.6 repeating. Then we're going to go here. There. And last one. Sorry. Probably should have typed these in, but that's okay. So 2.5, 2.9, 2.99, as we're getting closer and closer to 3, what's our function approaching? Not 0. 0.5. Okay, see it's 0.6, 0.52, 0.50, 0.500, 0.5000. It's getting closer and closer to 0.5. Yeah. These numbers are coming from plugging this into x for this function. Yeah.
Why isn't it coming right to the last 2 different numbers on the left?
Oh, sorry. 4th 9, sorry. Okay, good question. You have the 4th 9. So yeah, sorry, I didn't explain that very well. So these are my x values, Emily, and these are my outputs are. So these are my inputs, my outputs to this function. Okay.
How do you pick what numbers to put in for x?
We picked numbers getting close to 3. So right now we're investigating. So these are just the numbers that were chosen that kind of close to 3, closer, closer, closer. 3 is the close, not quite an asymptote, but yes. Okay, we'll explain why not in a second. Yeah. The 3 comes from, because this is why, good, you guys are ahead of the game, this is great, because this broken down, the x minus 3's cancel each other, so it's called a whole. So it's not defined there, but it's not an asymptote either. Because if I simplify it, like we are approaching that, because asymptotes, our lines take off, right? They don't come towards it at all. They actually shy away from it. This one, we're coming up to it, open dot, leaving it. Yeah, exactly. It's a point of discontinuity. Okay? So that's what we're looking at. And the limits help us identify where those points lie. Okay? So we're going to get to the limit part in a second. You guys are asking great initial questions. Okay, so now I'm just going to do kind of the same little chart here for x greater than 3. So here we go. So I'm going to go 3.5, 3.1, 3.01, 001. Okay. And then again, 6 decimals, 0.400, 0.476290. 0.497, 512, 0.499, 750, 0.499, 975. Okay, so the idea is that if we plug 3 in, we're going to get an error because it's not equal to that. But we can find the limit of this point as 2 lines are approaching it from each side. So let's just kind of, this picture is actually kind of a line. Okay, just for sake of quickness here, 1, 2, 3, with an open dot right there at 3. Okay, now this line is coming up from the left, and it's approaching 3 as we get close to 3. So as we get closer to 3, we get really close to half. So this line right here would be like a half. As we're coming from 3.5 from the right side and coming closer to 3 downward, again, we get really close to 1/2. Okay, the 0.4999975. So they're getting both really close to 0.5, which is 1/2. Okay, and actually, let me see here. This is actually in the picture I wanted. Let me see my next page here real quick. Yeah. Okay, so sorry, let me actually draw the better picture. I have it right here. So the better picture is this guy here. Because we still do have an asymptote where? At 1. Because 1 is still, can't be canceled, nothing, right? So we still have one at 1. Okay, let's see here. This guy goes like this. And then we get over here to 3, right here. We have, here's 1/2. We have an open dot here, and this one goes like this. So it's not, it's open dot there, it's discontinuity, like Morgan said, but we still can evaluate that limit by what's happening as it approaches from this direction and this direction. We can estimate what it would have been with a limit. Okay, I guess is the best way to say it. Okay, so now we're going to get into the notation part. All right, so how do we read or say a function written as a limit? Okay, so this right here, limit of this is how you'd read it. Limit of x minus 3 over x squared minus 4x plus 3 as x approaches 3. X approaches 3 is equal to, which we just got, 1/2, 0.5. That's how you'd read that notation. Okay, just kind of the general. Whenever I say general, that means with like variables, like not with no numbers. In general, limit as x goes to a, or x approaches a, of f of x equals our limit, L. Now, there's kind of two options, but I'll get to in a second. But when you're finding a limit, there's two things. You can evaluate it at A. If you can plug in A is what you're approaching. Okay? You can plug in A and find your limit. If you plug in A and it gives you error or 0, 0, we need to do stuff from our warm-up. We need to simplify and see if I can make it possible. Okay? And then if you can't, then you can have does not exist. The limit may not exist. Okay? And I'll show you what I'm talking about in those examples coming up here. So example 1. So limit as x approaches 5 of x squared plus 2x minus 3. Okay? Two things to consider. Can I evaluate the limit at A? So can I plug in 5 and have it, is there any issues? Do I have any fractions? Do I have square roots? So right now, I can simply just put 5 in. Does that make sense? So I can simply make x equal A, or approaching A, which is 5. Okay? So for this example, I'm just going to have limit as x approaches 5, and I plug in 5 squared plus 2 times 5 minus 3. So this limit, 25 plus 10 minus 3 is 32. That limit is 32. Now listen, is this a continuous or non-continuous limit? Like, what makes continuous happen? Like, from that first example, why was that one not continuous? There's an error, we had a 0 over 0, or we cancel the whole, right? This one, there's any canceling? No, this is just a continuous function, and this is a spot on that function. So when we evaluate that limit for that spot, it's going to be 32. Okay, and that's a continuous answer. We'll get to continuous in a second. Okay, so again, two things to consider when you're looking at a limit. Can I evaluate the limit at A? So can I plug in A and effectively? This one was number 1, yes. so we did it. Number 2, if I can't, can I further simplify the equation? That's what we're getting to later. Okay, so that's kind of things to consider when you're evaluating your limits. Sure.
So for that, you would just write the limit of non-existent.
For the one we just did,
Yeah.
the limit does exist. Right, because we can evaluate it at that point. The limit's 32. It is continuous for the one we just did because there's no hole that doesn't have a point discontinuity. Yes, because it doesn't cancel.
How would you write that?
32. Yeah, limit as x approaches 5 for that function is 32.
We don't have to say it's continuous.
No, you don't have to say it's continuous. I just want you to know that it's continuous based on when we get further into things. And we'll get into interval. So this one we can just say we'll have different intervals because we're gonna have pieces. We're getting ahead of me, but for right now we're just evaluating the limit at 5. At 5, the limit is 32. Not necessarily. Yeah. Okay. Yes. But it's not really why. It's more like the limit is 32. But we'll get to that. Okay, so these are the properties limits I took from the book here. I just kind of screenshotted it. So these are your properties. I can post this on our Google Classroom as well, so if you don't want to copy these all down right now. But what they are is that it's just properties of limits. So it's like, for example, if I have a limit of f of x plus g of x, I can break them up and evaluate them individually as separate limits. Okay, same thing with subtraction. It's just trying to think of the best way of why. It'll help you with the stuff later, but it's just kind of the basic idea of what you can do with limits. So again, if you're subtracting them, then you would just do it like that, separate them. Multiplication, of a constant, seek the constant. You can just put the constant in front because constants are not affected by limits. Why are constants not affected by limits? Exactly, they don't have a variable, that they don't affect the variable. Okay, if you're multiplying two functions, you can just put them simply, separate limits multiplied, same thing with division, same thing with exponents, and then same thing with radicals. Okay, we're going to do these things next. I don't think you need to write these down, so don't worry about hurrying to write these down. Okay, exactly like log laws, same type of thing. Except for I think these ones are probably a little bit easier. Like they're not special. Okay, all right. So then there's the list. These are the list of the rules, and then just here, if limit as x goes to a, x equals a. So this is just saying that if you're taking a limit of a constant, it's just the constant. So if I took the limit of x approaches 12 at 4, so here's an example. Limit x approaches 4 to 12. Limit x approaches 7 of 12, it doesn't matter. They're all 12 because the limit's not going to change because it's a constant. Okay? It's a flat line, right, technically, so that's not going to change. Okay? That's what this is saying. Okay? Okay, then from property 6 and 7, we deduct the following. It's also saying that if you have x to the n and you plug in a, then you'll have a to the n. We'll get to that in a second. Okay, so let's get to some examples here. Which one are we on? What's that? Oh, yeah, we're on this one, yes. Okay, so example 2. Okay, says repeat of example 1, but we're going to use the properties now. So if I use the properties, this is what we're talking about. I can write this like so. Limit is x approaches 5 of x squared plus limit x approaches 5 of 2x minus limit x approaches 5 of 3. So I just broke it up by the properties. You can, but right now we're kind of being redundant, Morgan. So we're just doing this for practice of the properties. Okay, because we're going to get the same answer. Right, Raj? Yeah. Okay, so where does, like, what's this one? If I evaluate this limit here, what's that one? 5 squared, so 25, right? That piece is 25, plus this piece is 10, minus the 3, because the 3 doesn't change. Again, we get the same 32. Okay. Okay. So everybody good with writing? Okay. So now we're going to look at these two. We want to use the properties. Okay. So we're going to try to make a little room here. All right. So to use the properties, I'm going to go limit x approaches 1 of x to the 4th minus limit x goes to 1 of 5x squared plus limit x goes to 1 of 1 all over limit x goes to 1 of x plus of 2. So again, that's just using the properties. Yeah, Emily? Right, yeah, if we get the 1, that will work for now, but we're still in the basic stuff, so this is going to change. Okay, so then when I do evaluate that, 1 from x to the 4th is 1. 5 times, so that's a minus 5, plus 1 is my top. My bottom is 1 plus 2. I get negative 3 over 3. Negative 1 is my limit of this function as it approaches 1. Okay, so how do the properties work for radicals? What's that? Right, they can't be negative, but in terms of the properties for limits, all we do is we just kind of limit the inside. So we do this. Limit x approaches 3 of x squared plus limit x approaches 3 of x. We just kind of do the limits of each piece on the inside. So that gives me 9, because x squared, 3 squared, plus 3 root 12. And then, yes, 2 root 3 is your simplified answer, the limit. When it approaches, it depends if it's continuous, right? So, yeah, we're saying it approaches this number, but depending on if it's continuity or not. Again, that part's later, but right now we're just finding the limit for now. So we will, you guys are doing, you're asking good questions for the future, so. Yeah, no problem. So notice when we get something with 0 over 0, like the stuff where we had to cancel, okay, and we'll get that in a second, we have to simplify to evaluate that limit. Okay, that means the function is not continuous. So essentially, let me put it generally here. So if limit of x to a of f of x equals f of a. So this means if f of x, if I plug in a for x and I get the same thing, which we've been doing, which you've been asking about, that is a continuous function. So this saying is if I plug in a for x and they're the same thing, it's continuous. So that's what Morgan's been just asking me. It's continuous. You can also say it's continuous at a. So that means it's a solid dot. It's going through at a solid dot. Okay? Stuff that we get this is not continuous. And that's like our first example. Because if I plugged in 1, I would have got 0 over 0, which is not a continuous point. I don't know why it does this little weird thing, but and need to put a U there. Okay. Is there any questions on that now in terms of what continuous means?
It means you don't get a 0 or a error.
Right. So it means if you plug in your limit, like what you're approaching, and you get a number, then that's continuous. If you plug in that number and you don't get anything or an error, then it's not continuous, but doesn't mean there isn't one. I think it's what if it's what? 0 is an okay answer. Just 0 is okay. Because 0 is an acceptable answer. Okay? All right, cool. So you guys are doing good. All right, so, whoops. All right, here we go. So example 4. So this is what we're talking about now. I can't plug in 4. Because if I plug in 4, I'm going to get 16 minus 16 over 4 minus 4. I'm going to get 0 over 0. Okay, so that's a problem. So this is where we're going to go back to our warm-up today, and we're going to break it down. And we're going to say, okay, I can go x plus 4, x minus 4, over x minus 4, and these cancel. And so then we'll go limit, as x approaches 4, of x plus 4. We get 8. But it's not continuous there. That's the difference. Right. If you can't plug in right away, it's not continuous. Yes. Right. Yep. 8 is the y value of the point of discontinuity. It would be 4, 8. Because not all, this one is just kind of solvable, but it's just because we're using basic functions. So what this looks like just if you want to see the picture here. That's what the picture looks like. So it's just a nice continuous line with an open dot at 4, 8. Okay? Okay, so now this one, we get to our difference of cubes again, like we had in our warm-up. Okay, so again, if I plug in 2, I'm going to get 8 minus 8 over 4 minus 6 plus 2, which is also 0. So I get 0 over 0 again. So at this point, we need to see if we can do some more work. So how this breaks down is going to be x minus 2 times x squared plus 2x plus 4. Like that. All over x minus 2, and then we have a x minus 1. And this is still limit x approaches 2. So again, our minus 2's cancel. And we can plug in our x2 now. So we get 2 squared plus 2 times 2 plus 4 over 2 minus 1. Minus 2x. This part? Okay, I'm sorry. Okay, so then we have 4 plus 4 plus 4. We get 12 over 1, so our limit is 12. And again, that's not continuous because there's a hole there. But it does approach 12 from the left and the right. Okay, this one. Okay, I'm going to go ahead and see if you guys can try this. So our biggest problem is an H in the bottom. So we're hoping that we can get stuff up to the top to cancel the constants. The constants are the problem. Because if I have all H's on the top, what can I do? I can pull them out and cancel the H's off. So that's what we're looking for. So yes, when I FOIL this out, I'm going to get 4 plus 4H plus H squared, and I have a minus 4 on top. And then see, the 4's cancel. So we have, now, we have limit as H goes to 0 of 4H plus H squared over H. Everybody's got an H. So we can pull it out. And now these cancel, and now we can evaluate the limit. So the answer is 4. Yeah, Emily? Right, I pulled an H out of the top because right now I'm identifying as my main problem is I have an H in the bottom. So I want to see if I can cancel it off somehow. Okay, so yes, that's what we were looking to do, was to pull an H out. Okay, good. Any other questions yet? Sorry. This? This is an H. Yeah, sorry. Just handwriting. 4 plus H there. All right, ready for example 7? I think we only have 2 left. Yep, just 2 slides left. All right, so example 7. So now, again, I have the same issue. So I'm going to ask you, based off of what we did in our pre-calc review, what do you think we want to try to do here? Because right now I have an X in the bottom. That's a problem. What's that? Okay, we want to get rid of X in the bottom. And does anybody know any strategies? If we don't have anything, I can't FOIL. Conjugate. Yes, this is where we actually want to use the conjugate to the numerator. Remember, on the pre-calc review, you're like, why would I want to do the conjugate to the numerator? This is why. Okay, I want to try the conjugate to the numerator. So I'm going to go root X plus 1 plus 1. Okay? Do the top first before you do the bottom. Just because sometimes, like on this one, you're going to want to leave them separate. Because this becomes X plus 1 minus 1. So what do I have? I have an X. So now I have an X to cancel with this X. So these will cancel now. So now we're left with this. 1 over root X plus 1 plus 1. Now we can evaluate that. Okay? 0 plus 1 is 1. Square root of 1 is 1. 1 plus 1 is 2. So this limit is 1/2. Okay? And now we'll talk about, lastly, we're going to talk about the ones that don't exist. Limits that don't exist. Okay? So, right here is one that does not exist. 1 over X. I want you to not brain freeze, the other thing, whatever. I want you to brain tease. I want you to think about this. I want you to figure out, why doesn't that one exist? Can you think of a reason why? Okay, you can't simplify it. There's no way to get rid of the X. All these are great answers. Okay, there is no conjugate because it's not a binomial. But I see what you're saying. Okay? Okay? Well, think about all my other ones. All my other ones that we did, we found limits, and I told you that means that that function from the left and from the right approaches that point. Does that make sense? This one we're going at 0. What's 1 over x look like? Does anybody remember? Okay, well, let's look. What's 1 over 1? 1, right? Okay, let's go further. What's 1 over 10? 1/10, right? All right, what is 1 over 1/2? Lower. Right? 2. 1 over 1/2 is 2. So I would be here. So this is what it looks like. That's what that piece looks like. Let's look on the negative side. Let's look on the negative side. So if I have -1, what's -1 equal? -1. And look, it's going to have the same. Okay, can anybody look at this picture and figure out why the limit's really having troubles? Why it does not exist? What did you say, Alice? It's absolute 0. What did you say, Abby?
I don't remember.
Where's this guy going? He's going to a really big negative number. Where's this one going? They're not approaching the same thing. That's why. They have to approach the same number. That's what the other two things have been doing. Okay? You guys, it's not approaching 0. This is approaching infinity. This is approaching a negative infinity. They're going opposite directions, so they're not coming together. That's why you can't take a limit on it. Okay, so this one's limit does not exist.
Yeah, it's probably really easy.
All right, any class questions?